And thanks for having me. Today I will be talking about cipher algorithms and enhancing them with natural language. I suppose it's June the 19th there in Australia. It's pretty late here actually. So anyway, don't have it's to be honest, this paper that I've done is a remnant of work that I originally did at Hofstra probably nearly 11 years ago or 12 years ago. It was just an idea that I came up with, and I figured, you know what, this was an idea that I wrote down quite well, and I meant to publish way back when, but I didn't get to it. So this paper will talk a little bit about the idea and the proposal that I had. I did go and actually try it to see if it works, and it did, just as a quick trial. But I think you'll find, everyone here will find this kind of interesting, because we've all used Wi-Fi at some point or another. And the idea of hacking a Wi-Fi network, for example, and are they hacking us, is obviously one of those that you're at an airport Wi-Fi or anywhere you may be, you're always kind of thinking that, oh gosh, maybe they're hacking me, so I can't go to this specific website because of the security there. And so I introduce a new layer for networking, and we'll talk a little bit about that today. The 6 things that I'm going to basically cover are these, and the introduction, of course, which I kind of already spilled the beans on. Stream ciphers, and I'll give a little bit of background on what stream ciphers are. I'm actually more into natural language processing, and just this is somehow overlapped with what I normally do in natural language. So we'll cover natural language encryption and what that would incur, or how one could use natural language encryption. Finally, I'll go over kind of my proposal and what I think would really help out for a networking cipher algorithm using natural language. Finally, I'll cover stream reliability and conclusion, and then lastly, thanks, with giving time for questions and comments. So before I get started, I want to make sure, I guess, Lisa, you can hear me okay?
Yeah, I just
Okay,
realized
right.
I'm going to mute now. So yeah, everything's fine. It looks great.
Okay.
Sound great. Okay.
All right, perfect. All right, awesome. All right, the introduction. So very generally, most of us, like I said, have done this or used this at some point, but there are specific algorithms that are generally created, and this is not just for Wi-Fi, in general for the public devices we use, Internet of Things and so forth. The Wi-Fi networks use algorithms generally to protect passwords. Some of the popular Wi-Fi algorithms that are out there, believe it or not, they're very easy to download. They're all open source, and you can typically find them and use them as an attacker to get the password being transferred between a Wi-Fi network and the router. Generally, these types of attacks, on the order of nearly 1 million or more per year, are successful. When I say successful, these are known attacks that are done on Wi-Fi networks in general, whether it be home networks or whatever it may be. And of course, back 11, 12 years ago, we were still some of us were still using web encryption. And so I brought that up as an easy to hack encryption. But, there's, and I'll get into this, where there are different types of encryption. Of course, we moved over to WPA and WPA2, which you'll see when you connect. But those aren't necessarily 100% secure either. So first and foremost, what is a stream cipher? In other words, what algorithm are we using to protect the communication between the computer and the router? Typically, that is a stream cipher, and it's called a stream cipher is just a symmetric encryption algorithm. And when we talk about symmetric, we're just talking about it uses the same, or the algorithm uses the same keys to encrypt and decrypt the password. And so in order for it to do that, the kind of password or the shared secret is something that's shared between the sender and the receiver. Now, when I say the shared secret, I'm talking about the part that's used to encrypt and decrypt the password, not the actual password itself. So that's important. And then, what will happen though, is very much with humans, in order to keep a secret, oftentimes it's not secure at all. In other words, that specific, let's say, key to encrypt and decrypt, oftentimes it's not so secret. So those secrets get out, and of course, publicly, even on websites and things like that, those types of secrets are there, kind of available, and of course, then it leads to an attack. If we talk about kind of why are these algorithms public? There's this principle called the Kirchhoff's principle, touched on by Stallings et al. In 2017, that basically talks about, hey, these algorithms should be public. And there's an argument there, and actually most cryptographers, which are the people that build these algorithms and build the decryption and so forth, encryption, the decryption, they all subscribe to the same idea that these algorithms should be public. And the reason why they think, well, one would think, well, the algorithm shouldn't be public, because then, of course, anyone can get the algorithm attacked. But the way the most cryptographers, or the people that build these algorithms, think is that the algorithm's fine. Let's just have that out publicly, so that any company that wants to provide Wi-Fi or a stream cipher algorithm, they can use it. But where the hard part should exist is in a different layer. This is kind of what everyone subscribes to. So in that case, they say, well, let's put more kind of emphasis on some other parts of the equation, right? And when I say the equation, it's the encryption, decryption part that does not necessarily include the algorithm. Rather, we say, well, let's put several layers on kind of how we could decrypt and encrypt. And this may be using random digits or bit shifting and other types of measures. So generally, stream ciphers hide the fact that a local language, for example, is used as the extra layer. Now that extra layer, when I talk about bit shifting, digit use, and randomness, oftentimes the extra layers are going to be done with the idea in mind that it's a local language. In other words, if I'm going to use an XOR, and I know it's going to be all characters from the English dictionary, or English characters from the words that exist, or the words that exist in an English dictionary for American English, for example, it's okay to assume that, but that has led to kind of algorithms, it leads to one more way that algorithms can be broken down. Because, if I already know that the language we're using is English, well, I just run a huge kind of vocabulary of potential characters, and then I can run over them several times and, of course, get the password. So my work is basically first a survey of a few algorithms that are stream cipher algorithms. It talks about a little bit about the weaknesses and advantages of both of them, or actually in the paper there's 3 or 4 of them. I'm going to present 2 of them today. And I also then propose a way that a natural local language can be used, along with what we call a noisy foreign language and natural language processing, to make decryption much more difficult. All right, so with that, I'm just going to jump right into stream ciphers. So a stream cipher, again, is the algorithm that's used, the generally publicly available algorithm that's used to protect network or Wi-Fi passwords going back and forth. So that is generally, we say stream ciphers, but just to be clear, it's just a pseudo-random generator. Now, when I say pseudo-random generator, it sounds like, kind of a complicated word. It's not really that complicated. If you look at the picture, this is kind of what happens at a simple level. So first, I have this key And I have to basically generate this key. And this could be just some random number. So if we use bits, for example, this um, key that's been generated here is 11010. So that key is the same. And like I said before, it's something that's kind of shared between the key generator, the input, and the decryptor. And it's the same thing. So 11010 in this particular example is the key generation or key that's been generated randomly. Now, the plain text, in this particular case, the input is 01011. Now, I'm just showing the bit version of this. Of course, plain text would be some other, if I were to decrypt the 01011, those could be letters, for example. Now, those, that input, the key generation or the key that's generated is applied onto the plain text. So if you see here, the 01011 is the input, then the key is 11010, which is the generated and random generating one. And that gives me a bitwise operation, and this is an XOR operation of 10001. Right, so then that's my cipher stream. That's the thing that gets passed back and forth. And then I use the same cipher, or sorry, the same key generator, right, which would be in this case on top of 1001, the cipher. I put the key back on, and then there I get 01011 back. So it's basically a very straightforward and kind of, it seems very easy, right, to crack. The idea really is like, yes, okay, this part is known, and that's why I think cryptographers say, and people that build these networking algorithms say, well, let's just make it public, because this part isn't the hard part. In other words, if they get the public algorithm, they're not really cracking anything. And I guess they're right. Right? You can't really argue with that. This is pretty straightforward. So I'm just XORing 2 bits together, or two strings together. All right. So when we talk about stream ciphers, there are different types of ciphers, and this you can visit the paper for. Stream ciphers and block ciphers are generally vulnerable. And again, this is due to word and letter frequency. So if a cryptographer, or if let's call the person an attacker, or we call them, the cryptographer is the one that actually builds these algorithms, but sometimes the attacker has all of this information that a cryptographer would normally have. If the cryptographer, if the attacker, let's call them, is in, let's just say, the United States, and a typical, like, very highly populated place in the U.S. where, and I would say even for the most part, anywhere in the U.S. If I'm the attacker and I'm going to attack some or try to attack some network somewhere, let's say the Starbucks network, if I do that, I'm almost certain, and I think all of you could probably understand too, that pretty clearly, if you were to try that attack, you would just try it on the English alphabet. So that then comes down to a frequency. And one would say, all right, well, how frequent are these words, or how frequent are these letters in the language? And when you get down to some languages, or specifically English, the frequency is very clear. And we'll see that in a second. But that's where the attack idea comes from. Now, if I'm sitting there in that Starbucks cafe, and I'm not plugging Starbucks here, so it could be any cafe or any place that you're at that has Wi-Fi, you have access to it. The idea is that if I'm sitting there as an attacker, I really have 2 or 3 algorithms that are already published online. Basically, that like I said before, the XOR algorithm using RC4 or LFSR are out there already. And for those of you that use Linux, I mean, I've used Linux all my life, ever since I began computing. Typically, there's these 2 programs that come with Linux by default installed, or at least in the Ubuntu repositories, Wireshark and AirTrack-NG, that directly use these algorithms. And all you have to do is tell it, all right, well, I want to do it in English. And so when you do that, you're at a cafe in US, Starbucks, or you know, the Cafe Nero in the UK, for example. There you can just run Wireshark and AirKNG, which is actually one of the things I did just to test this thing. And you'll see you can break it, right? It starts off and it tells you, or it asks you which algorithm, which language you want to choose. And of course, it just goes through the different potential words on a vocabulary list, which would be, you know, the highest potential passwords. And that gets updated automatically all the time. This is what it looks like from the if I were just to, from the natural language processing side. Again, that's what I do. And generally what we do, we look at all kinds of things like this. So unigrams, bigrams, trigrams. So if you don't know what that means, unigrams, if I'm talking about characters, it just means one character. If I'm talking about words, it means one word or one token, it's called in natural language. And, you know, oftentimes the, you know, those unigrams are stop words. But of course, we try to remove those stop words, which are words like the, and so forth. We remove all those out, and then we kind of come up with a frequency. So here's the frequency of unigrams. In other words, one word, or the frequency of words that exist in English tweets. And specifically, we're showing letters here just to get an idea of how I would tag. So, you know, I'm not showing the words here, but the words typically, you know, the most frequent words are things that you would imagine in English that are most oftentimes used, like store and supermarket, things like that. But, you know, the words are important, no doubt, but what's really important from the encryption side, in other words, the two encryption algorithms that I spoke on, is the unigram distribution of characters. In other words, the frequency. And so we see, for example, here, just looking at English tweets, the letter E has quite a few. In other words, most words have the letter E in it. And I don't know how many of you remember this show or have seen this show called Wheel of Fortune. But if you've ever watched Wheel of Fortune, and it's an American show as well, Pat Sajak oftentimes will ask ask a contestant on the show, and what basically your idea is to solve a puzzle given letters. And at the very end, one of the things they'll do is ask, all right, what letters do you want to try as your first go? And way back when, it used to be the case that you had to tell them the most frequent numbers, and most people already knew those by when they went to go play Wheel of Fortune, or not numbers, letters. So they would say R, S, T, O, N, and E. You know, the vowel would be E. The consonants would be R, S, T, L, and N. These days, if you ever watch Wheel of Fortune, which is now, I don't think it's even hosted by Pat Sajak anymore, but the idea is that they just give it to you because they know. So R, S, T, O, N are the consonants, and E is the most frequent letter or vowel used. And they will oftentimes just give you that on Wheel of Fortune and let you choose like the next letters. So I bring up that little kind of anecdote because it really shows the power of how just using the most frequent consonants and vowels can really, you know, affect someone coming to an outcome. And as particularly on Wheel of Fortune, it helps you solve the puzzle. Well, with a Wi-Fi network, it helps you, if you're an attacker, it helps you solve the password. Okay, natural language encryption. Again, what I normally do is natural language, and all of these things are kind of the pipeline of what we can do or how we attack the natural language processing problem. And so typically natural language processing, especially from the marketing level, it's known as unstructured text. From our standpoint of view as researchers, we typically see it as just corpora, or, and yes, you could call it unstructured text, even though we don't actually call it that. But what does that really mean? It just means a document, any document from anywhere that does not have a specific structure to it. So thus we call it unstructured text. But I think the idea is, if you just think tweets, for example, are oftentimes natural language. Conversations between, speech conversations between a speaker or two speakers That's unstructured text. Even the Constitution, right? That's unstructured text to a certain point as well. There is some structure to it. You have articles and so forth, but and Bill of Rights, for example, those types of things. But oftentimes in legal text, you also get a lot of unstructured text. And the structure to it may just be the category. I may have just a category of some text, but actually, for the most part, the writing and the natural language, in other words, the person that's writing this stuff in English, they're applying specific rules that we know in grammar. And then, when you speak a native language, you just speak it. You don't necessarily think about those rules. But oftentimes, one of the ways we process all of that type of text that has been written by a native speaker, generally, we just use the rules. And so those rules are often, first and foremost, before deep learning, we were using finite state transducers or FSTs, which would be very straightforward. Okay, well, I know parts of speech are here, so every sentence uses a noun and a verb, and every noun and verb has a noun phrase and a verb phrase, and then you keep going down from there. That's how FSTs generally work. But nowadays we have even more exciting kind of statistical models, which are typically based on deep learning, which make it even easier to find words in their context. So when we talk about natural language used or local language being used, typically what will happen is like we saw the frequency, the letters are transferred into bits. So you typically have a bitwise representation of words. And the stream ciphers are used to process the plain text. Now, the plain text, or what we call plain text language encoding, is simply taking those letters, getting the bitwise, and then adding or getting the bitwise representation of each letter or the entire word, however you want to do it, and then putting those together. Now, given those public algorithms, if I just use XOR like I did before, and that 10110 might represent just an 8, of course, then I have to add all of those together for, let's say, the word, I don't know, Atlanta. So for each one of those letters, I have a bit representation. So I add all of those, and then I XOR them with some specific key. And what will happen is there's typically a cryptographer that's sitting there between the LAN user and some device, right? And the device typically is going to be the router, which is the MR in the little picture here. And they'll, this is all bitwise information, so bits are going across the network, and so the monitor or the computer that's there monitoring that traffic will first, put what's known as a replay attack, kind of cut the communication off between the LAN user and the router, and when they cut that communication off, the wire LAN user or the actual user that's trying to get the information for themselves will attempt to make that new connection again to the router. And whenever they do that, of course, they're trying to transmit the password again, and that's done using this bitwise representation of what the password was. So that's really kind of how it works. So that bitwise representation again is based on typically a local language, which is like English, and it's just adding the things together and XORing. So it's a very straightforward algorithm, and if it's using a language, it's even easier. So here's the idea. For example, if I have these alphabetical letters A through Z, my encryption, in other words, what I would apply as the stream cipher, could be something like this, and this is obviously very straightforward. So I take each letter and I basically just apply another letter. So here, for example, the A corresponds to the Q, the B to the W, and so forth. And so the word attack, for example, would be QZZQEA. And then, of course, what goes over the networking path is the bitwise representation of QZZQEA. So not too complicated, right? And as long as I have just, an alphabet and the English alphabet, there are 26 letters. So the 26 letters just get, if I just use something like this, there's not much to it. So pretty easy to decipher. This you've seen and we've seen, I would say, in the news. This is previously done by Al-Qaeda, for example. There's a few articles, you can check the paper out. And this surprised me because I didn't know it. But some of the original Al-Qaeda texts that were used in both the UK and some other attacks were done using foreign languages. So, they would communicate basically in the language that was known by them. And then, indigenous languages as well, which is what I work in normally for NLP. I work in Quechua, Shanika, and other number of languages that are specific to a very specific region. And so those languages are less known, and they become a very good deterrent. And I don't know if any of you have heard of, kind of what went on in World War I and World War II, where we had specific languages that were used for Morse code. So kind of the same idea. I'm looking to add on language as a deterrent for the person that's trying to break in or break the signal between two users. All right, so lastly, not lastly, the next step, proposal. I think I've already touched on it, but just to be a little more formal, and again, you can look in the paper to see the more formal kind of definition of this. But the idea is really, inside of the these routers or the devices that use them. So inside of your laptop or inside of the router, right now we're just using the stream ciphers, and there is an extra deterrent phase of WPA, for example, which seems to be pretty good. But again, it's not all foolproof. One of the things, or what I'm proposing here, is that we add noise in. And the noise, very much like in natural language processing, what we'll do, we'll add in noise in the natural language processing to train an algorithm so that the algorithm knows of more of the negative examples rather than just the positive ones. Oftentimes when you train a model, you want balanced data. And if I were just to train a natural language processing model with positive data, it wouldn't really learn much. It would be very lopsided and always give me one type of information. So if you just think about this from the English standpoint of view, those of you that have heard German before and actually read some German before, you can in many ways see it as a noisy form of English, because both German and English share a lot of the roots, and those are called morphemes or lemmas or stems in English. So if you were to just take the stems from English and take the stems of German, you would almost find a somewhat similar vocabulary. And so German could be considered a noisy form of English, as does Dutch and other kind of closely related languages. Vice versa, you look at Portuguese, Portuguese could be considered a noisy form of Spanish, or Spanish could be considered a noisy form of Portuguese. So that's what my proposal is. We have a layer already that's there. You don't actually have to do anything, in the sense that we don't have to add a brand new kind of algorithm or update to all of the devices. The only thing that has to be updated is the key, and the key's vocabulary. So those lists, since they're already being updated online, you just basically create a new ciphertext algorithm that uses 2 languages or more. And those 2 languages, of course, and the password that's created would have to kind of be known by the user as well. So this is an important piece. FBI does this quite a bit with scrambling, and they especially did it back right after the 9/11 attacks. So the 9/11 attacks, of course, for the U.S., was a new kind of, event and something they really reacted to immediately. And one of the things that they did was to begin to um, communicate between the FBI, begin to communicate between themselves using more types of scrambled communication techniques. And one of those was taking the mobile phone signals and introducing different languages and things like that as well.